Welcome to the next lesson. This is Chemical Equations and Reactions Continued. Specifically, we're going to be talking about the 5 types of reactions and how to predict the products of those reactions. We're going to run through some new vocabulary pretty quickly, and then we'll get to our first type of reaction. Okay, the first thing we need to review is what a compound is. Remember, that's a substance composed of 2 or more elements. Okay. Decomposition reaction. This is one of the 5 types of reactions. They don't go in any specific order. It just so happens that decomposition is listed first, so that's the one we're going to go with. The decomposition reaction is one that results in 2 or more substances being formed from a single substance. Remember, in biology, decomposition or decomposers were things that broke down nutrients. Same thing in chemistry. The decomposition reaction started from one thing, and that thing was broken down into 2 or more things. Okay, a double displacement reaction, sometimes called a double replacement reaction, is one where the positive ions of 2 compounds are exchanged. That's why it's a double displacement, is because 2 compounds switch their cations. A single displacement, or sometimes called single replacement reaction, is one where an element replaces another element. Then we have a synthesis reaction. You've seen this word before in photosynthesis. Synthesis means to build something up. So this is actually the opposite of the decomposition reaction. It has a couple of names that it can go by. One of them is a composition reaction. Another one is a combination reaction. So here we have composition. That's the one that most easily shows you that it's the opposite of a decomposition reaction. And so that's when you have 2 or more substances coming together to form a single substance. So decomposition was one thing becoming 2. This one is 2 things becoming 1. Then we have a combustion reaction. And that's when all the substances in the compound are combined with oxygen and heat is released. Okay, an element is a substance that cannot be broken down or decomposed into simpler substances. We know that a mixture is different than a compound. It's 2 or more substances or compounds that are not chemically combined, and so they don't have a fixed set of properties. A solution is a homogeneous mixture, meaning that it looks the same all the way throughout. And then substance, which we have used multiple times throughout our definitions. A substance is a sample of matter that has a uniform set of properties and a definite composition. So those would be these 2 things. Remember, way back at the beginning we talked about pure substances and mixtures. These are the pure substances. So anytime we say that word, we're either talking about an element or a compound. Okay. We have 7 rules for determining the states of matter in a chemical reaction. This hasn't been important up to this point, but it's going to start to be. You're going to need to know in that chemical reaction what state of matter the chemical is in. And so here's how you're going to be able to predict that most of the time. If it's an element, then you just need to look at the periodic table in our classrooms. We have a key that on that periodic table that lets you know what state of matter the substance is in. If it's part of a metallic compound, then it's most likely a solid. If it's part of a non-metallic compound, it's most likely a gas. If it came from a solid and a gas, it's most likely a solid. If it's an acid, it's going to be aqueous. If it's a solid, liquid, or gas combined with water, then you'll have to look at solubility rules, which we have not learned yet, so I will give those to you for now. The reactants of a double displacement reaction must be aqueous, and then you can check the solubility rules for the products. Again, we haven't done that, so I will give you the state of matter for the products, but you need to know that the reactants in a double displacement reaction will be aqueous or dissolved in water. So the first type of reaction that we're going to look at is a single displacement reaction. And in a single displacement reaction, the more active element, which I will tell you what that means in a little bit, will take the place of another element in a compound and set the less active element free. So here's the general formula for a single displacement reaction. You're going to have an element plus a compound. That's a key identifying feature of a single displacement reaction. So if you see just a single element by itself adding to a compound, you know that you're looking at a single displacement reaction. And you're going to create a new element and a new compound. And here's how you do it. We're going to say that the element is letter A in this example, and the compound is compound BC. Alright, so that means it's made up of element B and element C. Element A is going to kick element B out. Alright, so that element B is by itself, and now A is paired up with C. This A in that case would be the cation. Alright, so it's got to be some kind of a metal. Alright, so the A comes in and it kicks the B out. Alright, so let's look at a couple of examples here. We've got potassium, and here I have HOH. That is just a different way of writing water, and we're writing it that way so that you can see what the cation and the anions are. Okay, so here this first hydrogen is obviously the cation, and then this hydroxide is the anion. Okay, so the potassium is a metal. Metals tend to lose their electrons and become more positive. Alright, so that means that they're going to become cations. So potassium's going to come in here and kick this hydrogen out, and it's going to pair up with the hydroxide instead. So we're going to have potassium hydroxide, and then notice I've got a little 2 right here. That's because hydrogen ends in gen. It's diatomic. It can't be just a single hydrogen. So it's going to partner up with another hydrogen to make a molecule of hydrogen gas. Okay? Here's another one of those. We've got zinc and we've got hydrochloric acid. So again, we've got our cation as the hydrogen, and we've got our anion as the chlorine. So the zinc is going to come in here and kick the hydrogen out and pair up with chlorine instead. So the hydrogen is going to become diatomic, and here we'll have ZnCl2. Now where did that 2 come from? Because it's not over here. Okay, every single time that you create a new compound, you need to check the charges. That needs to be your very next step. As soon as you have created your compound, check the charges. So let's see, up here, potassium has a +1 charge, alright, and hydroxide has a -1 charge. So when you crisscross and reduce, they just cancel out. Alright, now zinc has a +2 charge, and chlorine has a -1 charge. So when I crisscross, I have to bring that 2 down. Okay? Now this last one here is a little different. These first 2, the element was a metal, which means that it was going to function as a cation in our compound, because metals like to lose their electrons. But here we have a nonmetal as our element, and nonmetals gain electrons, so they're going to function as the anion. That means that this chlorine is not going to kick out sodium, because sodium is a cation. Chlorine is going to kick out bromine over here, because bromine is the anion. Okay, so the sodium is the cation and the bromine is the anion, and so the chlorine is going to come in here, kick out the bromine. Alright, so the sodium is still the cation, which means it's still going to be written first, because cations are always written first, and now it's going to be paired up with chlorine. Notice there's not a 2 here. Okay, remember, any time that we make a new compound, we need to check the charges. So NaCl, sodium is a +1, chlorine is a -1, so when I crisscross, the 1's cancel. So there's not a 2 over here, alright? Now the bromine, it is a halogen, and all of the halogens are diatomic, so that's why there's a 2 there. Okay? So really, we're just coming in and kicking the first element out if it's a cation, or if it's a metal, or we're going to kick the second element out if it's going to function as an anion because it was a nonmetal. Okay, now let's talk about what that more active and less active element stuff was talking about. This is called the activity series, okay? And it tells you what the more active elements are. Okay, so the activity is going to increase as you move up the activity series, which means that any element that is higher than another element in the activity series is capable of kicking it out, like we saw up above. Okay, so chlorine would be able to kick out bromine because chlorine's more active. Zinc would be able to kick out hydrogen because zinc is more active than hydrogen. So look over here, you see how chlorine is above bromine? That means that chlorine is more active than bromine is. And here's zinc on the list, and here's hydrogen down here. So zinc is more active than hydrogen, therefore it can kick it out. If, however, you have a reaction that has a less active element, maybe iron, for example, trying to kick out a more active element, magnesium, it's not going to happen. Okay, that reaction is not going to happen at all. All right. Now that's the overall table. Now within each of these little blocks here, we have some extra information, and that extra piece of information only applies to the elements within this little block. Okay, so here, this is for the overall table as a whole, and this is just for this little block of elements that we're talking about. These elements here can react with cold water and acids to replace hydrogen, and they react with oxygen to form oxides. Okay, so we can make some metallic oxides with these if we react them with oxygen. And if we react these guys with cold water or an acid, then we replace the hydrogen in that situation, okay, which we already predicted because all of those are more active than hydrogen anyways. Okay, now within this block, they react with steam. Okay, steam is the gaseous form of water. That means that the water had to boil in order to become a gas. So we need to have a temperature at which that steam is going to apply. So that's going to be 100 degrees Celsius or greater. Okay, so water is going to boil at 100 degrees Celsius, and that's when it's going to turn into steam. So if they give you a temperature in the reaction, and that temperature is 100 degrees Celsius or greater, then you're going to have steam or gaseous water, but not cold water. Cold water we're going to consider to be anything less than 100 degrees Celsius. Okay, so they'll react with steam and acids to replace the hydrogen, or they can react with oxygen to form oxide. So just like this block up here, except the water has to be above 100 degrees Celsius in order for it to replace the hydrogen. Otherwise, it won't happen. Okay, this one down here, they won't react with water at all. Okay, so you could drop a sample of lead into water and nothing's going to happen. Okay, they will react with acids though to replace the hydrogen in the acid, and they can react with oxygens to form some metallic oxides. Okay, so here we have a new set of elements, and they all can react with oxygen to form oxides. Then we have some pretty unreactive elements here, and sometimes they will form oxides. And then over here we have our halogens, and notice they are actually in the same order here as they are on the periodic table for their activity. Alright, so hopefully that makes sense to you, the overall activity series and then the qualifications for each little block of elements here. No, you do not have to memorize those. You will be given an activity series to look at, or there will be one up in the classroom for you to use. Okay, so here's basically what I just talked about in the activity series. This gives you your definition for it. It tells you that it is only for single displacement reactions. Not all metals will replace each other. Okay, only the more active element can replace a less active element. It's in your notes on page 112. That may change. And just because you can write a chemical equation doesn't mean that it's actually going to work. So here, if we did aluminum versus zinc, aluminum is more active than zinc, so it can replace it in this reaction here. Aluminum would kick the zinc out, and then the aluminum would pair up with the chlorine, and the zinc would be on its own. But if I did a reaction with cobalt versus sodium, cobalt is not more active than sodium on the activity series, and so cobalt can't kick the sodium out. So this reaction is not possible. Instead, we would write no reaction here. Okay, so let's do some practice. We're going to predict the reactions and balance them. If a reaction will not proceed to completion, which means if it doesn't happen, then you're going to write no reaction. Okay? So we have here zinc plus water, and that water happens to be at 50 degrees Celsius. So why don't we consult our activity series, and that's something you need to get in the habit of. Any time that you have a single displacement reaction, you need to look at the activity series to help you out. How did I know this was single displacement? Again, we have an element plus a compound, okay? That is our signifying characteristic, okay? Alright, so we have zinc right here, and it says that it will react with steam, but not cold water. That means that the water needs to be at least 100 degrees Celsius before anything's going to happen. Here, the water's at 50 degrees Celsius, so what should we predict over here? No reaction. Okay? RXN is just abbreviation for reaction. Alright, let's do the next one. We've got tin plus oxygen. Okay, so here's tin right here, and it says that it will react with oxygen to form an oxide. Okay, so what is an oxide? Basically, they're using nomenclature to create a class of compounds. Oxides, remember IDE is for a binary compound, so they're just saying that it's a binary compound that contains oxygen. And look, we have an element here and an element here. One of them is oxygen. So to make this an oxide, we're just going to put those two elements together. Okay, so here are the possibilities that we could get for our products. Now, why do I have two here? Okay, remember that tin has a possible oxidation state of +2 or +4. Now we have a solid tin here, which you need to remember that solid tin, the metal, has no charge at all. All elements and compounds are neutral. So really this has a 0 charge. But we know that once it becomes an ion, a cation over here, that it's going to give a 2 or a 4 cation. Alright, we just don't know which one. So you're going to have to predict the product for both of them. Okay? So if we look over here, you know that oxygen is going to be a -2. So now we just have to figure out what kind of tin do we have. Is it the +2 or the +4? Okay, so if oxygen's -2, then there would normally be a 2 down here. So why isn't there? Because we have the +2 version of tin. So when it crisscrossed down here, the 2's canceled out. Alright, so over here, we have a -2 charge for oxygen, and we would have brought that 2 down here, but it's not there for some reason. And here we have a 2. Alright, well, if this 2 came from tin, then that means that it would have canceled out with the 2 for oxygen, and there shouldn't be anything there. So why is there not a 2 here, and there is one there? Well, it's because originally we must have brought a 4 down here and a 2 here, and the 2 from the oxygen would have reduced with the 4 so that we keep a 2 here and a 1 here. Alright, so we have predicted both possible products, and that's something that you need to be on the lookout for. If your element is one that's going to produce multiple cations, then you need to go ahead and predict the products that involve both of those cations. Okay. Alright, let's look at this last one. We've got cadmium plus lead nitrate. Let's go look at our activity series. Okay, Here's cadmium and here's lead. That means cadmium is more active than lead is, so it'll be able to replace it. Okay, so cadmium is going to come in here and kick lead out, so that we're going to make lead plus cadmium nitrate. Okay, now cadmium is only a +2 element. It doesn't have multiple charges, so that's where this 2 over here came from. Alright, and we have made lead the element because it got kicked out, so that's going to be solid because metals are solid according to our 7 rules for predicting states of matter. Okay, now here this is aqueous because this was aqueous. Alright, so it's just continuing doing the same thing over and over again. You take the first element here and we're going to kick out the other first element if they're both metals. If we had a non-metal, it's going to kick out the non-metal, the anion. Okay, the next reaction we're going to discuss is the double displacement reaction. Remember, this can be called double replacement as well, but in my class I will only call it double displacement. Okay, so here's the general way that you would see it. It's a compound plus another compound, which gives you a new compound plus a new compound. Here's a special situation that is also double replacement that we'll see sometimes. It's an acid plus a base, which gives you salt and water, and this kind of double displacement reaction has a special name. It's called a neutralization reaction. And the reason for that is because of the pH scale. I don't know if you remember this from biology or not, but we're going to look at it really quickly. Things that have a pH from 0 up to like 6.99 are acidic. Things that have a pH of 7.01 all the way up to 14 are alkaline or basic, and 7 is what we call neutral. Water has a pH of 7, and so it's considered a neutral pH. And so here, when we create water, we're going to get a neutral pH for products. So that's why this is called a neutralization reaction, because the outcome neutralizes the acid and base, with salt and water being the product. Okay, so here's another basic form. We've got AB plus CD, and what's going to happen here is the cations are going to switch spots with each other. Okay, so the element A is now going to partner up with D, as you see here, and element C is going to partner up with B, as you can see here. Okay, so here's some examples. We've got barium chloride plus sodium sulfate. So the barium and the sodium are going to switch spots with each other, and that means that sodium is going to partner up with chlorine, and then we've got barium that's going to partner up with the sulfate ion. Now remember, I told you anytime you make a new compound, you're going to have to check your charges. So over here you see chlorine's got a 2, but over here it doesn't. Okay, that 2 does not carry across the reaction arrow. Alright, so the sodium has a +1 charge, the chlorine has a -1 charge, so when you crisscross and reduce, they cancel each other out. Alright, and then barium here has a +2 charge, and we know that Sos, Cos, and Cros have a -2 charge, so when we crisscross and reduce, those 2's are going to cancel with each other. Now, this 4 right here, you might be wondering, well, how come this 2 doesn't travel across the arrow, but this 4 does? Okay, here's the reason. That 2 here comes from barium having a +2 charge. Alright, so this 2 is dependent upon the charge. This 4, however, is not dependent upon the charge of sodium, which we know is a +1 charge. This 4 is here because sulfur is an Ni, and this is the sulfate ion. So this 4 has nothing to do with charge, and because of that, it stays together across the arrow. Okay? Alright, let's look at the next example. We have silver nitrate and potassium chloride. So those, the silver and the potassium are going to switch spots with each other. So we're going to have the potassium pairing up with the nitrate ion, and we're going to have the silver pairing up with the chloride ion. Okay? Anytime we make a new compound, you got to check your charges. Okay? Potassium has that +1 charge. This is not a POBO or ASO. It's not a SOCO or CRO. It's all the rest. So it's got -1. So that works out there. Those ones will cancel. Silver has a +1 charge, and chlorine has a -1 charge. So those cancel out, and we're good to go. We do have some special situations here for a double displacement reaction. Here is one of these examples. We've got calcium carbonate plus hydrochloric acid here. And so when we switch the calcium and the hydrogen with each other, because this is a double displacement reaction, you're going to have your hydrogen partnering up with this carbonate ion here. So you get H2CO3. And then you're going to have the calcium pairing up with the chloride, and so we'll get calcium chloride. Now this, since it starts with hydrogen, that's an acid. This is carbonic acid. Well, as it turns out, carbonic acid is unstable, and it will quickly decompose into carbon dioxide and water. So it's going to break down into CO2 and water. That means that we've actually got two reactions happening simultaneously. So our overall reaction, if we put it all together, you'll notice that the carbonic acid cancels out, alright, and we end up getting these two products out of it. So we have a product here, and then we have these two products here. So we are going to write an overall reaction, okay? The final reaction gives us the calcium carbonate plus hydrochloric acid, gives us the calcium chloride plus the carbon dioxide plus the water. So you just need to remember that if you form carbonic acid, it's going to quickly break down into those two products. So you do need to memorize that. We have some more examples of similar things happening. We have potassium sulfite here, and we are adding an acid to it. So notice in both of these situations we're adding acids. So what's going to happen is the potassium is going to come in here and switch spots with the hydrogen, just like in all the double displacement reactions. And when we do that, we're going to form potassium nitrate and then sulfur dioxide and water. So what happened right here was that we actually produced sulfurous acid, and that is going to break down into sulfur dioxide and water, just like up here we broke down into carbon dioxide and water. So we just replaced the carbon with the sulfur. Alright, notice this is SO3. Alright, that's the sulfite ion. Okay, and then our last special circumstance is when we have ammonium chloride plus sodium hydroxide. This is a base, and that is something I want to address with you real quick. I should have said it back up here, but I forgot to, so I'm sorry. Anytime in this course you see base, you need to be thinking hydroxide ion. Okay, so we said that acids are always going to start with hydrogens. Okay, you need to put it in your mind that bases are going to be hydroxide ions. So anytime you see that OH, you are looking at a base. Okay. Anyways, so we've got this ammonium chloride plus a base, and it's a double displacement reaction because you have a compound plus a compound. Now remember, ammonium is one of your exceptions, so all of that NH4 is the cation. So that's going to switch spots with the sodium, and the sodium is going to switch spots with it. Okay, so we've got the sodium that's going to partner up with the chlorine right here. Then we would have NH4 partnering up with the OH. Okay, so we would have that NH4OH, and what's going to happen is it's going to break down into ammonia and water. So NH3 and H2O. Alright? So please remember that if you have any of these special circumstances happening here, that you're going to form these products here in a secondary reaction. Alright, so I don't want you writing carbonic acid, I don't want you writing sulfurous acid, and I don't want you writing ammonium hydroxide. I want you to predict the final products. Okay, so let's get some practice here. you'll notice that I have given you the word form, so that means in order to predict the products, you're going to have to remember your nomenclature so that you can get the formula from the name. Alright, so we've got sodium carbonate. Alright, it ends with 8, which means it's polyatomic, so it's going to have oxygens in there. Carbo is the stem, or excuse me, carbon is the stem, so we know there's going to be a carbon, and we know there's sodium in there. Carbon is an aldi, so that means it wants 3 oxygens. So let's see if you can come up with the formula for that. I've given you a lot of hints there. Okay, so here's what I came up with. Remember, Sos, Cos, and Cros are -2, which is why we have a 2 there. Alright, and then over here we have calcium hydroxide. See what you can do for that one. Okay, now we need to go ahead and do the double displacement. So the sodium and the calcium are going to switch spots with each other. So that means that the sodium is going to partner up with the hydroxide now, and the calcium is going to partner up with the carbonate. Okay, so we have something that looks like this, and now we need to check our charges. Okay, remember, anytime you make a new compound, you've got to check the charges. So we have here that sodium is +1, and we know that hydroxide is -1, so when we crisscross and reduce, those would cancel each other out. They would be understood. We don't have to write them. So this looks good. Then we know that calcium is a +2 charge, and we know that Sos, Cos, and Cros are -2 charge. So when those crisscross, they'll reduce with each other, and we'll get that. So we have correctly predicted our products on that one. Okay. Alright, let's do this one here. Take a second and see if you can come up with the correct formula for iron 2 sulfide and hydrochloric acid. Okay, so here's what we come up with, and I hope that you got the same thing. We have the +2 version of iron, okay? We know that sulfur is a -2, so when they crisscross, the 2's cancel and we get this. And then we have hydrochloric acid, so that's binary HCl. We know hydrogen's +1, chlorine's -1, so that's the formula we come up with. Now we'll do the double displacement. So the iron is going to displace the hydrogen. They're going to switch spots with each other. So the iron will be paired up with the chlorine, and the hydrogen will be paired up with the sulfur. Okay, so we end up with something that looks like this. The iron's paired up with the chlorine, the hydrogen's paired up with sulfur. Now, anytime you make a new compound, you check the charges. So we know that we've got the +2 version of iron, and we know that chlorine is a -1 charge. So when we crisscross, we need to bring a 2 down on the other side of the chlorine. Okay, now let's do this one. We know the hydrogen is a +1 charge, and we know that sulfur is a -2 charge. So when we crisscross, we need to bring a 2 down in between the hydrogen and the sulfur. Alright, and then that means we've predicted the correct products there. Okay. Alright, I want you to try this last one all by yourself. Okay. I'm going to give you a hint here. We've got hydroxide, which I told you earlier means we have a base, and we have an acid here. So this is that special kind of double displacement reaction where you have an acid plus a base. Okay. Okay, so here's what you should get. We have magnesium hydroxide. Remember, magnesium's +2, hydroxide's -1, so that's where this 2 is coming from, is up here. Sulfuric acid, sulfur is the non-metal, acid means it starts with hydrogen. Ic is the ending for if you have the number of oxygens you're supposed to have. Sulfur is an any and it wants 4, so that gives me the 4 oxygens there. Bit of nomenclature review for you. Okay, then we're going to do our crisscross and reduce, so hydrogen's +1, Sos, Cos, and Cros are -2. And then we'll do our double displacement. Okay, so the magnesium and the hydrogen are going to switch spots with each other. So the magnesium is going to pair up with the sulfate ion over here, and then you're going to have a hydrogen paired up with OH, so you get HOH, which is the same thing as H2O. Okay, Anytime we make a new compound, we have to check the charges. Magnesium is a +2 charge, and so is Cos and Cros are -2, so those will cancel each other out. Alright, so hopefully that's starting to make some more sense to you now. Alright, the next type of reaction that we're going to look at is synthesis, or sometimes it's called composition, okay? So in this one, again, we have two or more elements or compounds that combine to form a more complex compound. So two things become one thing. Here is the general form. We have A plus B gives us AB. Now this one is not just a simple case of one thing switching out with another. In this case, we have actual reactions that we're going to have to memorize. I think there's 7 of them, okay? So I'm going to go through and do my best to try and help you see all of these things together so that you can understand what's happening. The first reaction here is metal plus oxygen gives you a metal oxide, or a metallic oxide. That's what I'll be calling it, okay? So metal plus oxygen gives you a metallic oxide. Remember, IDE is talking about binary, okay? Ox is the stem for oxygen, and so really all they're saying is take a metal and stick it together with oxygen so that you can form a 2-element compound here. Alright, so we've got magnesium plus oxygen gives us magnesium oxide. That's easy. The next one is kind of just the opposite of that. We have a nonmetal plus oxygen gives us a nonmetallic oxide. So here they've got carbon plus oxygen gives us carbon dioxide. Okay, so hopefully that's easy enough to remember. Then we're going to take the product of the first reaction, the metallic oxide, and add water to it. And when you do that, you get a metallic hydroxide. In other words, you are going to form a base. Okay, so we've got calcium oxide here. We could have taken the magnesium oxide from that first equation, and we're adding water to it, and then we're going to make a metallic hydroxide. So the metal in this case is the calcium, that's the metal, and then of course hydroxide is always the OH. Okay, and that's going to be a base because anything with hydroxide is a base. I'm going to skip this one for a second and do this one instead. We're going to take the non-metallic oxide from that second equation and add water to it, and we get an acid, which you could consider to be the opposite of a base. Okay, so the metallic oxide in water gives you a base, and the non-metallic oxide in water gives you an acid. Now, I'm hoping that this will make sense to you here because remember, the general formula for an acid from nomenclature way back when was this, HXYOX. And remember, the Y was the nonmetal. Okay, so that means that all along acids have been made with nonmetals. Okay, and so here's where that actually comes from. You would have a nonmetallic oxide adding to water, and that is what gives you the acid. The water is the source of hydrogens, and then the nonmetallic oxide is your source of the nonmetal and the oxygen. Okay, so here we have a nonmetallic oxide, sulfur dioxide, plus water, and that gives us our sulfurous acid. Okay, alright, so metal and oxygen makes metallic oxide. That metallic oxide plus water gives you metallic hydroxide, which is a base. Nonmetal plus oxygen gives you a nonmetallic oxide. That nonmetallic oxide plus water gives you an acid. Okay, so that gives you 4 reactions right there that are kind of linked with each other, as you can see. So hopefully that makes it more easy to memorize those 4. Okay, now we've known this one for a long time. Okay, metal plus a nonmetal gives us a salt. We learned that back in bonding when we learned about ionic bonds. Things on the left-hand side of the periodic table, which are metals, plus things on the right-hand side of the periodic table, the nonmetals, always give us salts, and they have ionic bonds. So sodium plus chlorine gives us sodium chloride. Okay, now let's talk about this reaction down here just a little bit further. It says, in order to know how many oxygens to give the polyatomic anion of the acid, that's this right here, just add up the oxygens on the left-hand side. Remember, all compounds are neutral. Okay, so what they're saying is I have 2 oxygens from the sulfur dioxide, and I have 1 oxygen from the water. And remember, the law of conservation of matter, you can't create or destroy matter, so if I've got 3 oxygens over here, I've got to have 3 oxygens over here. So that's how we knew to make that H2SO3 rather than, like H2SO4 or something, okay? However, that will not always work. You will not always be able to just count up the oxygens and have it work. There's only certain situations that will work on. I'm going to tell you what they are, but I'm going to give you another foolproof method that works every single time, no matter what the situation. Okay, so rather than counting the oxygens, this time we're going to use some math, and of course that's the method that's going to give us the right answer every single time. So I know you're not going to like it, but sometimes you're going to have to use it. What we're going to do is we're going to keep the oxidation state of the sulfur the same across the reaction arrow. So we need to figure out what the oxidation state of this sulfur is while it's part of this compound. Okay? Remember, all compounds are neutral. That means that their oxidation states have to add up to be 0. Okay? So we're going to do a little algebra to solve for that. Okay, so we want to know what the oxidation state of sulfur is, so we're going to leave that as a variable right now. We know that oxygen is always going to have a -2 charge, and we have 2 of them. So that means that we're going to have a -4 over here on the left-hand side. Alright, so we need to add 4 to both sides. Okay, so that means that sulfur has a +4 charge in this sulfur dioxide molecule. That means that sulfur has to have a +4 charge in the acid over here. Hydrogen has to have a +1 charge, but there's 2 of them, so we have a +2 charge total. Okay, so that means all together we have a +6 charge. That means that the negative charge has to be a -6, okay, all together. Now, if oxygen is a -2, then how many of them do we have to get -6? Good. We need to get 3 of them in order to get a -6 charge, because 3 times the -2 gives us this -6 up here, so that these will cancel each other out and give us a 0 or neutral charge altogether. Okay, so anytime that you need to know how many oxygens to give the acid, you need to go through this algebra method here, or you could do the counting. And again, there's a rule for when you know to do the counting and when you know that you can't do the counting, and I'm going to teach that to you a little bit later, but for now I just want us to get some practice on doing this algebra here by finding the oxidation state of the nonmetal. Okay, so we've done 4 reactions so far, and here are 2 more to give us 6 reactions. These are the reverse of some decomposition reactions. We have not actually learned these decomposition reactions yet. Those are going to come up next, but when we do learn those, the reverse of a decomposition is a synthesis or a composition reaction, and therefore the reverse of all of these reactions here are decomposition reactions. So you can take an acid and decompose it into a nonmetallic oxide in water. Alright, so let's go learn some of those decomposition reactions. Alright, so let's look at our decomposition reactions. Remember, this is when a single compound breaks down into more than one part. Okay? So the general formula is the reverse of our synthesis. It's when AB breaks down to become A plus B. Okay? And just like the synthesis reactions, there's going to be several of them that we're going to have to memorize. Okay? So the first one is if you have a metallic carbonate. Alright? Obviously, the metallic means there's going to have to be a metal. And now this carbonate here, that comes from your any-outy rule from nomenclature. Let's see if we can remember. 8 means that there's going to be an oxygen. Carbon means the nonmetal is carbon. And For it to be a carbonate, for it to have that 8 ending, that means that the carbon has the number of oxygens attached to it that it's supposed to have from the any-outie rule. Well, hopefully you remember that carbon is an outie, and if you don't remember that, you can just look on your periodic table to see. So that means that the carbonate ion is CO3 with a -2 charge. So we're just going to take a metal and attach it to the CO3 ion, and that's going to give us a metallic carbonate. Okay? Anyways, when you heat that, you get a metallic oxide and carbon dioxide every single time. It doesn't matter what the metal is, it's just going to stay the same. Now, heated right here, that's what this triangle represents. Okay? So anytime you see a triangle over your reaction arrow, that means heated. Okay? So our example here, calcium carbonate. Calcium's our metal, and then we've got our carbonate there. That's being heated, and then we get a metallic oxide. So the metal from over here is the same metal that's in the oxide. In order for something to be an oxide, remember IDE means binary, and ox means that the second element is oxygen. So metallic and then oxide. And then we get our CO2 gas. Okay? Okay, the next reaction is a metallic chlorate. Okay, so kind of the same idea as what we just did. There's going to be some metal, and then we are going to have the chlorate ion. So remember, the chlorine element is an outie, so it wants 3 oxygens to be able to end with this ATE ending. Okay, so there's what we're looking for. And when you heat that, it's going to break down into a metallic chloride. Okay, remember IDE is binary. Chlor tells me that the second element is chlorine. So you're going to have a metal and chlorine stuck together. And then oxygen. Now this right here is molecular oxygen, which means that it's the breathable kind. It's the kind that's in the air. So that is O2. Alright, so this is not the element oxygen, which would just be O, but this is molecular oxygen, which is O2. Alright, so here's our example. We have potassium chlorate, and that's going to be heated, and so we're going to break down into potassium chloride plus our molecular oxygen. Alright. Then we have acids. This is the reverse of one of our synthesis reactions. If you heat up an acid, it's going to break down into a nonmetallic oxide plus water. Okay, so hopefully you remember in our synthesis reaction, we had a nonmetallic oxide plus water creates an acid. So this is just the opposite of that. Alright, well, how did we know that there was going to be only 3 oxygens on that nonmetallic oxide? Okay, again, you could count the oxygens. So over here there's 4. That means over here there has to be 4 total. You know that one of them has to go to the water, so that leaves 3 left for the nonmetallic oxide. Again, that's not always going to work. So here are the rules to see when it will work. Okay, POs, BOs, and ASOs. You can count them, you can count up the oxygens, but only if there's one less oxygen in the acid than there are hydrogens. Let me give you an example. Okay, so here you would see there are 2 oxygens on this side. One of them belongs to the water molecule and the other one belongs to the nonmetallic oxide. I'll get to how I knew there was 2 phosphoruses in just a little bit. But you just need to know if you have one less oxygen than you do hydrogens in the acid, then you're allowed to count for POs, BOs, and ASOs. If that's not the case, then you'll have to figure out what the oxidation state is of your nonmetal and make it the same on the other side and then calculate how many oxygens you need. If your acid has a SO, CO, or CRO in it, then you can always count the oxygens. You don't have to do the math at all, which is nice. And if it has any of the rest, then you can never count the oxygens. You'll always have to do the mathematical method. Okay? So let's go back and review that mathematical method again. Okay, so let's say that we are doing H2SO4, sulfuric acid. I just told you if there's SOs, COs, and CROs, then you can just do the counting method. So before we even go through the math, we should be able to figure out what our nonmetallic oxide is going to be. You know that one of these oxygens has to go to the water molecule. That means the other three go to the nonmetallic oxide. So we should get SO3 at the end of all of our math if we do this right. Okay, so again, we know this is a neutral molecule and we are trying to find the oxidation state for sulfur. So we know hydrogen is a +1 charge and that there's two of them. We don't know sulfur, so we leave it as sulfur. We know that oxygen has a -2 charge and there are four of them. So 4 times -2 is -8 plus +2 is -6. Now in order to solve for sulfur, we would need to add 6 to both sides. That means that sulfur has an oxidation state of +6. So it also has to have an oxidation state of +6 on the product side as well. So here's our nonmetal. It's SO and there's some number of oxygens. Okay? So you can rationalize this to yourself. You can say this sulfur is +6 and we know that oxygens are -2. So how many oxygens of -2 charge can balance out a +6 on the sulfur? The answer is 3. There has to be 3 oxygens in order for them to balance. Or we could do just a little bit more math. We know that the sulfur is the +6. We know that oxygen has a -2 charge and we're trying to figure out how many oxygens, that's this X right here, and that it all has to add up to be 0. So we're just solving for X. That means we're going to subtract 6 from both sides. And now we'll just divide both sides by -2. And we get X equals 3. That means there has to be 3 oxygens. So either way you choose to do that, if you just kind of want to talk yourself through it this way, that's fine. Or if you want to solve for X this way, then that's cool too. You're going to get the same answer either way. Alright, but what do you do if your answer comes out to be a fraction? Okay, let's say that you just went through the math that we just did, but you got a fraction instead of the number 3. Okay, I'm going to take you through an example where that will actually happen to you. Okay, if that happens, you're going to make the numerator of the fraction the number of oxygens, and the denominator of your fraction is going to be the other nonmetal. So here's your example. What if we had phosphoric acid, H3PO4? Okay, well what that's going to make is water and diphosphorus pentoxide. But how would you know that? If you were trying to figure this out, all you would know is that it's going to be PO something, okay, some number of oxygens. You might not even realize that you're supposed to have a different number of phosphoruses. Okay, so here's what you do. You're going to remember that this is a neutral molecule, and so you're trying to find the oxidation state of the nonmetal, which is phosphorus. So you know hydrogen's the +1 charge, and there's 3 of them. You don't know what phosphorus is yet, and you know that oxygen is -2 charge, and there's 4 of them. So 4 times -2 is -8, plus a +3 gives us -5. So you add 5 to both sides, and that means that phosphorus has to have a +5 charge in this molecule. Well, that means that it must have a +5 charge on the product side too, whatever this is. Okay, so we need to figure out how many oxygens then are going to be attached to our nonmetallic oxide. Well, if you know that phosphorus is +5 and oxygen is -2, then how many oxygens of a -2 charge each can balance out a +5 charge? Well, there's no whole number answer to that. Okay, so that means you need to do the math. So we're going to say the 5 for the phosphorus, and we've got -2 for the oxygen, and we're trying to solve for X, and all of it has to add up to be 0. So we're going to subtract 5 from both sides, and now we'll divide both sides by -2. And so X must be 5/2. Okay, that means that 5/2 would have to be the subscript on oxygen, but you can't have a fractional number of oxygens. So in order to get rid of that, what you're going to do is give the numerator to oxygen and the denominator to the nonmetal. So 5 belongs to oxygen and 2 belongs to phosphorus. So you're going to get P2O5 as your nonmetallic oxide. Notice if you tried to count your oxygens with this molecule, the original acid, which is right here, you would say, okay, there's 4 oxygens on this side. That means there has to be 4 over here. One of them goes to the water, so that means we should have PO3. Well, you would be wrong because we just figured out that it's actually P2O5. Alright, so I want you to do this one on your own so you can get a little bit more practice on this. I want you to predict the products of this. We are decomposing an acid. Your acid has some of all the rest polyatomic anions, which means you cannot count the oxygens. You're going to have to go through mathematically and figure it out. Take a second and do that, and then when we come back, we'll see if you got what I got. Alright, here's what I've come up with. Of course you're going to get water, and then here's the nonmetallic oxide. Again, you could not count the oxygens to figure this out. We need the oxidation state for chlorine, so we go through the math and find out that it's +5. Now we need to know how many oxygens we're going to make. So we take our 5 for the chlorine, and then we know that the oxygens are going to be -2 each, and we're trying to figure out X, how many oxygens, and it all has to add up to be 0. So you move the 5 to the other side and get -5, and then we'll divide both sides by -2. That means X equals 5 halves. So the numerator goes to oxygen and the denominator goes to chlorine. And so we end up with Cl2O5, which is dichlorine pentoxide. I hope that you were able to go through that and get the same thing as what I was. Alright, here's some more examples of the reverse of a synthesis reaction. Some binary compounds will decompose back into the elements that form them. So here we have a metallic oxide, and it will decompose into a metal and oxygen. That's the reverse of your very first synthesis reaction. Okay, we could also add electrons in order to decompose something. So here, electrons are going to split the hydrogen from the oxygen, so you'll get hydrogen gas and oxygen gas. Or here, we'll have sodium chloride. You can add electricity to it and get sodium the metal and chlorine the gas. Notice that this sodium chloride is liquid. That doesn't mean that it's dissolved in water. That means that they took actual salt and melted it so that it became molten salt. Here's what that would look like. So if we ran electricity through that, then we could have sodium, the metal form, and chlorine gas. Of course, that would be a really dangerous experiment to do because this gas, again, is toxic, and this will explode and burst into flame once it touches the moisture in the air. And here are some other synthesis reactions, and if you did the reverse of them, then you're going to get your decomposition. So we could take that metallic oxide, go back to metal and oxygen. We could take the non-metallic oxide, go back to a non-metal and oxygen, and so on and so forth for each of the ones that we had done before in the synthesis section. Alright, that leaves us one last reaction, which is going to be the combustion reaction. Okay, the fifth and last kind of reaction is the combustion reaction. In a combustion reaction, hydrocarbons are what's going to be combusted. The name says exactly what's in that compound. It's a compound that contains carbons and hydrogens. It can contain other elements like oxygen, sulfur, nitrogen, but it must contain carbon and hydrogen. Okay? And they're going to use the word to burn. Okay, so heating is for decomposition, not combustion. Burning means combustion. So when they say that a hydrocarbon was burned, then they're saying that it was combusted in a combustion reaction. You can only burn something in oxygen, okay? You cannot have a combustion reaction without oxygen. That's why there's no fire in space, because there's no oxygen up there. So here's an example of a basic form of a combustion reaction. You've got some kind of a hydrocarbon, so these X's obviously represent some number that we don't know yet. So you can have some number of carbons bonded to some number of hydrogens to form a specific hydrocarbon. They are burned in oxygen to create carbon dioxide, water, and heat. These are always the products of a combustion reaction. No matter what the hydrocarbon is, these are always the products. So here's an example one. You've got this specific hydrocarbon, which is butane, plus oxygen, and then you're going to get carbon dioxide, water, and then of course heat. Alright? If we do add nitrogen into the hydrocarbon, then you're going to get this nitrogen dioxide in addition to these three. It doesn't replace the carbon dioxide, it just is another additional product. If we add sulfur into the hydrocarbon, then you'll add sulfur dioxide to the products as well. Here's an example of what that might look like. So here's a hydrocarbon that has incorporated nitrogen into it. So you're going to get carbon dioxide, water, nitrogen dioxide, and then as usual heat. Okay. And then down here we've incorporated sulfur into this hydrocarbon. So we get carbon dioxide, water, sulfur dioxide, and we need to add heat. Okay? So, and that's just as simple as that. Combustion reactions are not that difficult. Any kind of hydrocarbon you can think of added to oxygen, you always get the same three products: carbon dioxide, water, and heat. Okay, that is the end of our predicting reactions unit. I hope that you understand it more now than you did before. If you have any questions, please come see me for tutorials, and as always, thanks for learning with me. Bye.